Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 10th video lecture. And last time we defined what it meant to be Riemann-Stieltjes integrable and some background definitions that helped us define Riemann-Stieltjes integrability for a function. And I'd like to start off today by looking at an example. So we're going to let F go from A to B. Instead of A to B, let's give a specific A to B. Let's say from 2 to 7 into R. And we're going to define it by f of x is equal to 3. And we're going to let alpha of x be defined on 2 to 7 as well. And what it's going to be defined to be is x squared. Now I'm going to look at originally a specific partition of 2 to 7. So I'm going to say let strip P be equal to 2, 3, 5, and 7 be a partition of 2 to 7. Then, if we look at the upper Riemann-Stieltjes sum with this particular partition for our f and for this alpha, here again f is bounded and alpha is increasing, then what that's defined to be is the sum as I run from 1 to, here it would be 3, of big M sub I, and then it would be delta alpha sub I. That's the way we have it defined. Where M sub I, you might remember, is going to be the biggest value for f of x over the sub-intervals that we have here. And the delta alpha sub I, which I'll expand upon, the sum as I run from 1 to 3 of big M sub I, the delta alpha sub I is going to be alpha of x sub I minus alpha of x sub I minus 1. For this particular example, this is going to be equal to, well, the big M is always 3. This is a constant function. And then it would be times alpha of x sub 1, that would be alpha of 3, minus alpha of x sub 1 minus 1, which is alpha of x sub 0. X sub 0 is 2. And then plus, again, it would be 3 times alpha of, here it would be 5 minus alpha of 3. And then it'd be plus 3 times alpha of 7 minus alpha of 5. And so this is going to be 3 times, here this is going to be, remember alpha squared is whatever we give it, so this is 9 minus 4 plus 3 times 25 minus 9 plus 3 times 49 minus 25. And then what that's equal to is going to be 3 times, this will be 5, plus 3 times 16, plus 3 times 24, and that ends up being 15, plus 18, plus 72. There's 90. I think it's 105. No, it was 135, so I made a mistake. Oh, here, this is 48. So that's 135. That was my mistake. Okay, so that's what we get for this calculation. Similarly, the lower Riemann-Stieltjes the lower Riemann-Stieltjes sums, what I should say, with this partition of this to f with respect to this alpha, is also going to be equal to 135 because the little m involved in the summation of this lower Riemann-Stieltjes sum is nothing more than 3. Times this delta of alpha sub I. And we get the same sum as what we had before. So that's the reasoning. Before I move on, when I come back here and look at our previous work, you might notice that this 9 here would cancel out with this 9 here, this 25 here cancel out with this 25 here. We end up with 3 times 49 minus 3 times 4, and that is indeed the answer. So that would be a quicker way of doing this upper Riemann-Stieltjes sum in this case. Oops. Sorry. Give me a second just to look back here at this board just in case we needed to. Okay. All right. I want to talk more about this example in terms of some of the background items that we used in defining the Riemann-Stieltjes integral. And so here, we'll say for any partition, not just the one that we had, script P of the closed interval, it was from 2 to 7. Okay? The upper Riemann-Stieltjes sum with respect to that partition F and alpha will be equal to the sum as I runs from 1, well, it could be the n of big M sub I, and then it would be delta of alpha sub I, which equals to the sum as I runs from 1 to n. Here the f, we're thinking of it to be the same function we talked about before. The constant function is 3, so its maximum value over any subinterval is going to be 3. And then the delta alpha sub I again is going to be the alpha x sub I minus alpha x sub I minus 1. And that's going to be equal to, well, it's going to be 3 times alpha x sub 1 minus alpha x sub 0 plus 3 times alpha x sub 2 minus alpha x sub 1 plus, and we'll keep going all the way up to the last term, which is going to be 3 times, and it's alpha x sub n minus alpha x sub n minus 1. Okay. And this turns out that a lot of these terms will cancel. Here's an alpha x sub 1, here's a minus alpha x sub 1 to be multiplied by the same thing, and because of that multiplication by the same thing, they will cancel. As a matter of fact, everything will cancel, except we will be left with the alpha x sub 0, which is being subtracted, and here the alpha x sub n. So it turns out to be 3 times alpha x sub n minus alpha x sub 0. But in our case, we know what x sub n has to be for a partition. X sub 0 has to be for a partition. That would be 3 times alpha. X sub n here is going to be 7 minus alpha of 2. X sub 0 is A. X sub n is B. AB. So this is equal to 3 times, remember what alpha does, it squares things. So this is 49 minus 4. That ends up being 3 times 45, which in this case is 135. It isn't always the case that the upper sums are going to be independent of the partition we take, that they're always going to be the same number no matter what partition we take. So you need to be careful of that. But anyway, in this case, because we have a constant function, it works out to be that way. Okay. Well, similarly, for any partition script P of 2 to 7, the lower Riemann-Stieltjes sum with that partition F and alpha will be equal to, the I runs from 1 to n of the little m sub I, delta alpha sub I. It's going to be the same thing. It's going to be 135. So, turns out then that the sup of the lowers and the sup and the nth of the uppers, they're going to be 135. So what we get is that the lower Riemann-Stieltjes integral of f with respect to alpha is going to be equal to 135, and that is equal to, and the upper Riemann-Stieltjes integral of f with respect to alpha is also equal to 135. And so since the lower Riemann-Stieltjes integral is equal to the upper Riemann-Stieltjes integral, that says that f is Riemann-Stieltjes integrable with respect to alpha. And the way we write that is this way. With f, or I should say, the integral, Riemann-Stieltjes integral of f d alpha equal to 135. This was a very simple example where f was a constant, so it wasn't so hard to compute. A little harder to compute in other situations, but that's just an example of Riemann-Stieltjes. Well, next, I want to look at some facts having to do with partitions with Riemann-Stieltjes integrals. And definitions of certain types of partitions. So namely, we'll start off with this definition. It says, we say that a partition script P star is a refinement of a partition P, okay, if P is contained in P star. So P is a subset of P star. And another definition, given two partitions let's say script P1 and script P2. Let me be a little bit more specific here. Of A and B, okay? And in the refinements, each partition was of the integral A to B, so closed interval. The common refinement, that's what I'm defining, common refinement of P1 and P2 is script P star equal to P1 union P2. That's the common. Okay, here's a theorem. It says if script P star is a refinement of P, then the lower Riemann-Stieltjes and sum, I should say, with P, F, and alpha is going to be less than or equal to the lower Riemann-Stieltjes sum with P star, F, and alpha. And it turns out that the upper Riemann-Stieltjes sum with P star, F, and alpha will be less than or equal to the upper Riemann-Stieltjes sum with P, F, and alpha. And what I'll do, we'll do a proof, but what I'll do is I will prove that the lower sums, the fact about the lower sums, and leave the upper sums to you. We can prove that the upper sum with the refinement is less than or equal to the upper sum of just P with the students. It would probably be a homework problem. So, So we want to prove this inequality. And so the way we'll do it is the following. So we suppose P star has only one more point. Than P. So it's a refinement that just has only one more point. So this is kind of like a case. Okay? And let's say that one more point is denoted by, so let this extra point be X star, and suppose X of I minus 1 is less than X star, which is less than X of I, where X of I minus 1 and Xi are both partition points, if you will, in P and P star. So I'll write it out this way, where X of I and, X of I minus 1 and X of I are two consecutive partition points of script P. Okay. Now, here's what we do. For notation's sake, we define, let W sub 1 equal to the infimum of F over all x's. But here, I'll say over, this way I'll write it, x element of, I'll write this way, x of I minus 1 is less than x is less than or equal to x star. That's W sub 1. Okay. Then we'll let W sub 2 be equal to the infimum of all f of x's where we have that x star is less than or equal to x is less than or equal to x sub I. Okay. Now, here's what we're thinking. We can note this, and I think it's pretty clear to everybody. Note that m sub I, this little m sub I, which is the minimum value of f from x sub I to, x sub I minus 1 to x sub I. This guy is definitely going to be less than or equal to W sub 1, and m sub I will be less than or equal to W sub 2, where m sub I is equal to the infimum of f of x for x sub I minus 1 less than or equal to x less than or equal to x sub I. Okay, look, just in terms of explanation, it's not necessarily something you have to include in the proof. Here is x sub I minus 1, and maybe this is x sub I, and here is x star. Okay? What is m sub I? M sub I, so let me just draw this F. Let's say F looks like this. Okay, this is my F. The m sub I is the lowest point, the lowest y value, stacked y value, right? That's the lowest y value over this whole region. Well, what we're saying is if you look at the lowest value over this region, maybe that's here, okay, and you look at the lowest value of this region, both of them have to be bigger than or equal to the lowest value of the whole region. Okay? That's all we're saying. All right. That tells us then, or hence, okay, hence, L, the P star, well, let me write this down. The lower sum involving the refinement F and alpha minus the lower sum involving P, F, and alpha. Okay, what's this going to be equal to? Well, remember, they're the same almost everywhere. The only time that they're different is just over the interval from x sub I minus 1 to x sub I. Everything else involved will be the same. And so their difference over this region is going to be W sub 1 times alpha x sub x star minus alpha of x sub I minus 1, okay? And then plus, it would be W sub 2 times alpha x sub I minus alpha x star, okay? And then from that, we would subtract the part that's in the lower, the thing that didn't take it away by the lower sum with respect to just P, which is going to be m sub I, little m sub I, of alpha of x sub I minus alpha of x sub I minus 1. That's what we'd have. So that's equal to this. We're going to expand that. So when I expand that, what I get is, that's equal to W sub 1 alpha x star minus W sub 1 alpha x sub I minus 1. Okay. And then it will be plus W sub 2 alpha x sub I. And then it will be minus W sub 2 alpha times alpha x star, okay? And it will be minus m sub I alpha x sub I, and it will be plus, I think, m sub I alpha x sub I minus 1. Let me make sure that my writing here is correct. Yep, that's what I got listed. And then I'm going to add and subtract the same thing so that we get this form into a more beneficial setting. So I'm going to say this is W sub 1 alpha x star. And then what I'm going to do is I'm going to subtract, okay, m sub I alpha x star. I'm going to add that a little later. But this term I'm going to write in, W sub 1 alpha xi minus 1, and then plus, here it is m sub I alpha, plus m sub I alpha x sub I minus 1, so this term is what I'm writing next. And then plus, I'm rearranging the term somewhat, W2 alpha x sub I, W2 alpha x sub I, and then minus, here's m sub I, alpha x sub I, okay, this guy, and then I have minus W2 alpha x star, that guy, and then I'm going to add this guy, m sub I alpha x star. Okay, so that's the term. We've rearranged these terms up here and subtracted and added the same quantity. And when we do that, what we can do is we'll get that this is the same thing as W sub 1 minus m sub I times the quantity alpha x star minus alpha x sub I minus 1, okay, and then plus W2 minus m sub I, and then that's times alpha x sub I minus alpha x star. Okay, so that's what the line above is equal to. It was by grouping, essentially. And so here's what I'm going to tell you. This is going to be greater than or equal to 0. Okay, and let me explain this. Remember, this guy is greater than or equal to this guy. And this x superscript star is bigger than x sub I minus 1, and alpha is an increasing function, so this is greater than or equal to 0. So this is going to be greater than or equal to 0. Similarly, this is greater than or equal to 0, and this is going to be greater than or equal to 0, and so we must get greater than or equal to 0. So in this case, that means that the lower sum with P star F alpha is going to be greater than the lower sum with just P F and alpha. And that was because this guy minus this guy was greater than 0. So this guy must have been bigger. That's what we got. Bigger. Now, when I say in this case, remember what case we're talking about. We're talking about the case where P star just has one more point. Okay. Well, it could have up to finitely many, whatever finitely many we're talking about. Points difference. Okay. Let's talk about that. If P star contains K more points than P in script P, we repeat this argument. Okay. K times and still B. That the lower sum with the P star partitions, the refinement, is bigger than or equal to the lower sum without the refinement. And so that's what I'm going to call the end of the proof in terms of with the lower sums. And again, I'm going to leave the upper sums for you. Okay, I want to move on to a theorem. Here's what it says. It says that the lower Riemann-Stieltjes interval, which is going to exist, is going to be less than or equal to the upper Riemann-Stieltjes interval, which is also going to exist for bounded F and increasing alpha. Okay, let's look at this proof. It's short. So what we do is we let P star, be the common refinement of two partitions, which we'll write as script P1 and script P2. Then, by the previous lemma, our previous theorem, okay, what we have is the lower sum with common partition is going to be less than or equal to the lower sum of, let's say, with P1, okay, the P1 is less than or equal to the lower sum with the common partition, the common refinement, F alpha, which is always going to be less than the upper sum with this common partition. And then by the part of the theorem I didn't do, that's going to be less than the upper partition, the upper sum with P sub 2, F, and alpha. That's what we have. Okay, what that gives us is the following statement. Hence, what we find is that L of P1 F alpha is definitely going to be less than or equal to the upper P2 F alpha. Okay, and that's true no matter what two partitions you take. And so that being the case, what we'll say is now by fixing let's say P sub 2 and using the definition of the lower Riemann-Stieltjes interval. Okay, what is that definition? This is equal to the supremum over all partitions of the lower sums. Well, here, remember, no matter what partition we have, it's going to be less than or equal to this upper partition, the upper sum, I should say, with P sub 2. So this upper sum is a supremum for the set of all lower sums. And so the supremum of that, the least upper bound, is going to be less than or equal to any other upper bound, which this is. So we have this statement. But now, that means that this lower, now looking at it another direction, this number, okay, is a lower bound for the set of all upper sums. So P sub 2, it could be any P sub 2, any partition. And so this number becomes a lower bound for this. And so the greatest lower bound of this, the set of all upper sums, is going to have to be bigger than or equal to this. So by definition, the greatest lower bounds of the infinimum, we have this lower Riemann-Stieltjes interval is less than or equal to the upper Riemann-Stieltjes interval. So that proves this fact. Okay, next I would like to do a statement that's an if and only if statement. Namely, as the theorem, we're going to let F, no, I should say it this way, sorry. A function F, when we're picking up the D value, is an element of Riemann-Stieltjes interval functions with respect to alpha on A to B, if and only if, for every epsilon greater than 0, for each epsilon greater than 0, there exists, I'm not saying for each, let's change this. For each epsilon greater than 0, there exists a partition script P, of course I mean it's a partition of A to B, I'll write that down, such that the upper sum with this partition minus the lower sum with this partition is less than epsilon. So it's an if and only if statement. We're ready to start the proof. I'm going to do the backwards direction first. So here I'm going to suppose for each epsilon greater than 0, there exists a partition of A to B such that the upper sum with this partition minus the lower sum with this partition, that difference is less than epsilon. And that's what I'm assuming. That's the hypothesis. What we want to show is that F is this Riemann-Stieltjes integrable with respect to alpha. We want to show F is an element Riemann-Stieltjes integral function with respect to alpha. That is, the only way we can do that, by definition, at this point. That is, we want to show that the lower Riemann integral of F with respect to alpha is equal to the upper Riemann integral, Riemann-Stieltjes integral, I should say, with respect to alpha. That's what we want to show. All right, well, note, this is kind of easy, that the lower sum, Riemann-Stieltjes sum, with P is going to be less than or equal to the lower Riemann-Stieltjes integral. Why? Because this is the soup of all of these guys. This Riemann-Stieltjes integral, lower Riemann-Stieltjes integral, is the soup over all partitions of these types of sets, which is going to be less than or equal to the upper, the previous fact, Riemann-Stieltjes integral, okay, which is going to be less than or equal to the upper Riemann-Stieltjes sum with P. Okay? That statement gives us that 0 is less than or equal to, here, the upper Riemann-Stieltjes integral minus the lower Riemann-Stieltjes integral, and it's going to be less than epsilon. And that's true because the difference between this and this is going to be less than the difference between the bigger, the numbers that are further apart, that is the lower sum and the upper sum. And the difference between the upper sum and the lower sum is epsilon. So this intermediate numbers difference is going to be less than that. And epsilon was arbitrary. And so since epsilon is arbitrary, what I'm saying is that no matter what positive number you give me, this difference is going to be less than that, okay? But yet bigger than or equal to 0. And there's a fact that says if that's the case for every epsilon, that means that these two quantities have to be the same, or this subtraction has to be 0. So let me write that up. This implies, since epsilon greater than 0 is arbitrary, then this implies that the upper Riemann-Stieltjes integral is equal to the lower Riemann-Stieltjes integral. And so that's half the proof. Now we're going to go this direction. well, let me make a conclusionary statement. So F is an element of Riemann-Stieltjes integral functions with respect to alpha. We'll do this version. Suppose F is Riemann-Stieltjes integral with respect to alpha, and we're going to let epsilon be greater than 0 be given. What we want to do is we want to show there exists a partition, script P, of A to B, such that the upper sum with respect to this partition minus the lower sum with respect to this partition is less than epsilon. That's what we want to show. That's the statement that we want to prove. Okay. Since F is Riemann-Stieltjes integral, then what we have is that the infimum of all the upper sums over any partition equals to the Riemann-Stieltjes integral of a Riemann-Stieltjes integral F with respect to alpha, which equals to the Riemann-Stieltjes integral and the sup over all p's of the lower sums, which equals to the lower Riemann-Stieltjes integral, which equals to the Riemann-Stieltjes integral. Okay? All right. So, that means that the integral of A to B of F d alpha plus epsilon over 2. Okay? So that's a little bit bigger than the Riemann-Stieltjes integral. Okay? And what we'll say is that is not a lower bound for the sets of all upper sums with respect to any partition of alpha. Okay? And that's over the possible partitions. Okay? That has to do with this infimum. This is a little bit bigger than the infimum, and so it can't be a lower sum. Okay? So what does it mean for this quantity not to be a lower sum? I have this parenthesis there. So there exists a piece of 2, this partition, so that is a partition of A to B such that, okay, so this was is a little bit more than the Riemann-Stieltjes integral. It's not a lower bound. So there's got to be something smaller than that. So it's that U, piece of 2, F, and alpha is less than this Riemann-Stieltjes integral plus epsilon over 2. Okay. Similarly, what we have is that the Riemann-Stieltjes integral of F with respect to alpha minus epsilon over 2 is not an upper bound for the set of all lower sums, partitions, P, F, and alpha. So there exists a piece of 1 that's a partition. Of A to B with an integral from A to B of F D alpha plus epsilon over 2. No, minus epsilon over 2. Okay, it's not an upper bound, so it's got to be something bigger than that. And this is this lower sum, piece of 1, F and alpha. Okay. And I want to make a comment about this just a little bit further. In particular, I'm going to add epsilon to both sides of this inequality. I'm going to add epsilon to both sides of this inequality. So, that means that the integral from A to B, f d alpha, plus epsilon over 2 is less than this lower sum with respect to piece of 1, f alpha plus epsilon. Now what we do is we look at the common refinement. So let P star be the common refinement of P1 and P2. Okay? Then we have that the upper sum with the common refinement, F and alpha, is less than or equal to the upper sum with piece of 2, F and alpha. And we know that this part is less than the integral from A to B of F d alpha plus epsilon over 2, okay, which is less than the lower sum of piece of 1, F alpha, which is less than or equal to the lower sum with the refinement partition, F and alpha. That's what we have. Okay. So this was less than, oh, I made a mistake. It should be less than epsilon, which is less than this, plus epsilon. So here I miswrote this part. So this guy right here is less than this guy. But this part is less than this part. So this lower sum is less than this lower sum. Okay. So that says this upper sum with this partition, this refinement, is less than this lower sum with this refinement partition plus epsilon. So we get the result we wanted by just subtracting the lower sum from each part of the inequality. Namely, that the upper sum of this partition, this refinement partition, minus the lower sum of this refinement partition is less than epsilon. And that's what we wanted. So that concludes the proof, and that's all I wanted to do today. Thank you very much for your time and patience.